Srimathy Srinivasan.
Louder?
Srimathy Srinivasan.
Okay, thank you very much. We'll work on it. But okay, motivic decomposition of projective pseudo-homogeneous varieties.
Okay, so this is the title of my talk. Let me just jump into details. So let's start with some notations. G is a semi-simple linear algebraic group over a perfect field K of characteristic P, and del sub G denotes the set of simple roots here. And associated to G, we have something called the Dinkin diagram. It's an oriented graph. Okay, and it turns out that the nodes of the Dinkin diagram are in one-to-one correspondence with the simple roots.
So you assume V is split?
Sorry?
V is split?
So no, in this case G is just semi-simple linear algebraic group, but then
The Dinkin diagram is overflowing.
yeah. So there's some, I'm not 100% accurate with the notations, but it is what it means. So the nodes of the Dinkin diagram are in one-to-one correspondence with the simple roots, which is again in one-to-one correspondence with the conjugacy class of maximal parabolic subgroups. And also the subsets of nodes of the Dinkin diagram are in one-to-one correspondence with the conjugacy class of parabolic subgroups. Okay, so these are like well-known facts about linear algebraic groups. Now we have the absolute Galois group denoted by gamma. It acts on the maximal parabolic subgroups inside G, and since the maximal parabolic subgroups are correspond to the nodes of the Dinkin diagram, we have an action on the nodes of the Dinkin diagram, and this action is called the star action. So if the star action is trivial, then we say that G is of inner type over K, otherwise G is of outer type over K. Okay, so let's recall briefly what flag varieties are. So flag varieties are varieties of the form G mod P. So it's the quotient of the algebraic group mod any parabolic subgroup. So when I say parabolic subgroup here, I assume that assume by default that they are reduced as schemes. So examples are like the projective space, Grassmannians, quadrics. They're all flag varieties. Okay, so now what are projective homogeneous variety? A projective homogeneous variety for G is some variety which, when you base change to the algebraic closure, becomes a flag variety. Okay, so these are basically twisted forms of flag varieties over the base field. Again, examples to keep in mind are Severi-Brouwer varieties corresponding to a central simple algebra. Okay, so let's just forget about the algebraic groups for now, and then I'm also going to talk about Chow motives in my talk. So let's just briefly recall the category of Chow motives. So it's denoted by Chow K comma lambda, where K is a field, lambda is a coefficient ring. The objects in this category are just triples X and P. So X is a variety over K. So when I say variety, I mean smooth projective variety over K. N is an integer, and P in this case is a projector in the endomorphism ring of the object X, which means like when you compose P with itself, you get P again. So I haven't said what the Hom sets are in this category. So the Hom sets between these two objects is this. So sorry. So what you do is you just take the dim X plus N minus mth Chow group of X cross Y, and then tensor it with this coefficient ring, and then you precompose and postcompose it with this projectors P and Q. Okay, so this is the Hom set, but again I haven't said what the how to compose the morphisms. So the composition works this way: if alpha is in the Hom between these two objects, and if beta is in the homomorphism set between these two objects, then you can compose alpha and beta this way. So what you do is you have the triple product X cross Y cross Z, and alpha is in the Chow group of X cross Y, beta is in the Chow group of Y cross Z. So what you do is you just pull back alpha and beta along the projections, projection along the first and second factor, and the projection along the second and the third factor, do the intersection product here, and then push it forward. Okay, so this is how the composition works. Okay, so this is about the category, and let me also briefly recall some properties in this of this category. So we have tensor product in this category. You can take two objects and then take the tensor product. It works this way. and also associated to an object in the category, associated to a smooth projective variety in this category, you have something called the motive of the variety. So motive of x denoted by m of x is just the triple x 0 delta x, and here the del x is just the diagonal inside x cross x. Okay, so it's a projector. And also there are other special objects. One special object is the Tate motive. It's just the motive of the point spec k 0 comma the diagonal, and you can also twist the Tate motive by an integer I. So the effect of this is just instead of 0 here you have an I here. Okay, and in general you can twist any motive by an integer I. So this is basically taking tensoring with Tate motive shifted by I. Okay, so the effect of this is just whenever you have n here, if it twisted by I, it becomes n plus I. Okay, so these are the operations you can do here. And you also have direct sum in this category. Again, I don't want to go into detail. You can decompose an object into direct sums of object. Okay, so now one of the common questions that we ask is if you are given an object in this category, how do you decompose the object into direct sum of other objects? Okay, so the answer is find a non-trivial projector, right? Whenever you have a non-trivial projector, so when I say non-trivial projector, I mean something that is not 0 or the diagonal one. So whenever you have a non-trivial projector P inside the endomorphism ring of the motive of x, then you can decompose the motive of x this way. Okay, for example, take the projective line. Then the endomorphism of the motive of the projective line is just the Chow 1 of P1 cross P1, and then it turns out that the class of this cycle, point cross P1, is a projector. It's a non-trivial projector. Therefore, you can decompose the motive this way. It turns out that the first summand is isomorphic to the Tate motive, and the second one is isomorphic to the Tate twisted by 1. Okay, so in general, you can also decompose the motive of projective space into a direct sum of twisted Tate motives. Okay, so these are some examples of how you can decompose a motive. Okay, so now the question is, if you want to decompose, you need projectors. How do we find projectors? A useful technique to find projector is by knowing whether Ross nilpotence principle holds, and I'll explain what this is. So we say that Ross nilpotence holds for a variety x over a field f if for every field extension E over f, the kernel of this base change map. So the endomorphisms of motive of x over f, so this is just like Chow x cross x, and this is the same thing base change to E. E is a bigger field. So the map is like take any cycle here and then you base change it to E. So if the kernel of this map consists only of nilpotence, then we say that Ross nilpotence holds for x. Okay, this is important for many reasons, and one of the important consequences is like it helps you find projectors in many cases. Okay, so once we know that Ross nilpotence holds, then there's a good chance like you may be able to find projectors in many cases. Okay, so now what is known about Ross nilpotence? We know that it holds for projective homogeneous varieties, which I just talked about before, and we also know that it holds for surfaces in characteristic 0, but we don't know if it holds in general. Okay, so how do we, our next question is how do we decompose the motives of projective homogeneous varieties? Okay, so and from now on throughout the rest of my talk, I'm going to assume that the lambda here, the coefficient ring, is a finite connected ring. An example to keep in mind is any finite field with q elements. Okay, and from now on G is going to be of inner type over K, and X denotes a projective homogeneous variety for G. So the goal is decompose the motive of X. Okay, how do we decompose the motive of X? Is it decomposable first of all, and so on. Okay, and how do we describe the indecomposable summands appearing in the decomposition of the motive of X? And again, another question is a decomposition unique first of all? It turns out that the decomposition is unique as long as the ring is a finite connected coefficient ring, and this principle is called a Squirrel-Schmidt. So Schmidt holds whenever whenever the decomposition of an object in this category is unique up to permutation. Okay, and for projective homogeneous varieties, it turns out that Schmidt holds. Okay, and also once there's also one special summand in the complete decomposition called the upper indecomposable summand. I'll just tell what that is. So a summand of the motive of X is upper if Chow upper 0 of M, and this by definition is the harms from the motive M to the Tate motive. It's just all the harms. If this set is not equal to 0, then the motive M is said to be upper. Okay, for example, the Tate motive lambda itself is upper, right? And but the Tate motive twisted by 1 or 2 is not upper because the harm set is 0 in that case. Okay, so this upper summand is unique because of Schmidt, and you denote this by U sub x. So the upper motive of the variety X is denoted by U sub x. Okay, it turns out that it contains a lot of information, and you can explicitly express the motivic decomposition of any projective homogeneous varieties in terms of upper motives. Okay, there's a theorem, and again I don't want to go into detail, but so now what I'm going, this is all part of the literature. Now what I'm going to do is, instead of looking at parabolic subgroups, which by definition was reduced, I'm going to look at parabolic subgroup schemes which are not necessarily reduced. So for example, look at G equals SL3. Let P tilde be the subgroup scheme defined by these equations. Then clearly the ring for P tilde is not reduced. Okay, so this is an example of a parabolic subgroup scheme. Okay, so the underlying reduced subscheme of P tilde in this case is the standard Borel, which is the upper triangular matrices. So what we see is that in characteristic P, subgroup schemes of G need not necessarily be reduced, and a parabolic subgroup scheme I'm going to define as some subgroup of G which contains the Borel and which is not necessarily reduced. Okay, so this is usually denoted by P tilde. So P tilde is a parabolic subgroup scheme, and for that P tilde, if I remove the tilde, then the letter P just denotes the underlying reduced subscheme of P tilde. Okay, so this is the notation I'll follow. Okay, so we have already seen what the flag varieties are. The flag varieties are just quotient of G mod parabolic subgroup which was reduced. Now I can generalize that, and I can look at what are known as variety of unseparated flags or VUFs. So these are generalizations of flag varieties, and what I do is, instead of taking P, I take P tilde and quotient G mod P tilde. Okay, so P tilde is a parabolic subgroup scheme which is not necessarily reduced in this case. So this is analogous, this is like a generalization of flag varieties. Okay, so this is again an example. Take SL3, and I'm going to look at this variety in P2 cross P2 given by this equation. Okay, so this is the G action on X and Y. Then it turns out that if you look at the stabilizer of this point in this variety, it is a parabolic subgroup scheme given by these equations, and again this is not reduced. Okay, so and also it turns out that the action is transitive. So X tilde is just the quotient of G by P tilde. Okay, and therefore this is a variety of unseparated flag. Okay, and what do we know about VUFs? So it turns out that they are not in general isomorphic to any flag variety. Okay, so there are only in certain cases VUFs are isomorphic to flag varieties, but in other cases they're not isomorphic to flag varieties, and also they behave very differently from flag varieties in terms of from cohomological perspective. So it seems like they don't have any relation with each other a priori. And also this is over the algebraic closure. So what about the twisted forms over base field? There's nothing much known about these varieties. Okay, so now the question is, how are they related? Is there any relationship between the VUFs and the flag varieties, or more generally, is there any relation between their twisted forms over the base field? The answer is yes and yes. So what I show is I show that their motives are isomorphic in the category of the category Chow k comma lambda. Again, the lambda here is finite coefficient ring. Okay, so so we know what flag varieties are. We know what projective homogeneous varieties are, and I said like the VUFs are a generalization of flag varieties. Now, what about the twisted forms? So corresponding to projective homogeneous variety, I can also define what is known as projective pseudo-homogeneous varieties. These are nothing but varieties over K, which when you base change to algebraic closure, it becomes isomorphic to a VUF. Okay, so you have flag varieties on one side, VUFs on other side, and then projective homogeneous varieties, which are twisted forms of flag varieties, and we have projective pseudo-homogeneous varieties, which are twisted forms of VUFs. Okay. Okay, so these are twisted forms of VUF, and what we can do is corresponding to a projective pseudo-homogeneous variety, I can define a projective homogeneous variety this way. So what I do is I take x tilde, then it is G mod p tilde over the algebraic closure. I can take the underlying reduced scheme for p tilde, you get G mod p, and you look at the corresponding homogeneous variety over over the base field, which is isomorphic to G mod p over the algebraic closure. So this way we get a projective homogeneous variety corresponding to a projective pseudo-homogeneous variety, and this is the notation. So if x tilde is a projective pseudo-homogeneous variety, x denotes the corresponding homogeneous variety. So we can associate a projective homogeneous to a projective pseudo-homogeneous variety. Okay, and I show that although they look very different, although they're not isomorphic in general, the Chow motives are isomorphic. Okay, so this I also show the following. So as a consequence of this, we also get what is known as we also get the Ross-Nilpotence and the Kroll-Schmidt holes for projective pseudo-homogeneous varieties, just like projective homogeneous varieties. Okay, now how do I show the main result? The main result that the motives are isomorphic is proven using this generic criterion for isomorphic motives. I call this generic criterion basically because this theorem works for fields of any characteristic K. So I don't care what the field underlying field is. So you take X to be a projective homogeneous variety for G over any field of any characteristic, even 0. Let Z be any geometrically split projective variety satisfying Ross-Nilpotence such that the following holds. Suppose if the upper motive of X and the upper motive of Z are isomorphic, and if the motive of X and the motive of Z are isomorphic over the function field of X, then I claim that the motive of X and motive of Z are isomorphic. So this tells you when the motives of two varieties are isomorphic, provided provided you know that they are isomorphic over their function fields, and provided that their upper motives are isomorphic. Okay, so again this proof is long, and this has many applications, one of them being the motive of X and motive of X tilde are isomorphic. So using this theorem I can just show that motive of X and X tilde are isomorphic. So I don't have a lot of time here, but I'm going to skip this proof, but I'm going to give you some examples and applications of this. Okay, so let A be a central simple algebra over K of degree n. Okay, and let B denote the central simple algebra of degree n, that is Brouwer equivalent to A tensored with itself p times. Okay, then in the category of Chow motives, with lambda being finite field coefficients, the following is true. So if X d1 d2 up till d1 comma a, so this is the variety of right ideals of reduced dimension d1 less than or equal to d2 less than or equal to up till dm in A. So this is a twisted form of flag variety over A, and this is again variety of right ideals of reduced dimension d1 d2 up till d1 and dm inside B. So this is again twisted flag variety for B, and then I show that these two motives are isomorphic, and the way I show it is by using the theorem that the motive of X and X tilde are isomorphic. So in this case, this B is just turns out that this B is just like A twisted by the Frobenius of Frobenius. So A tensor by with itself p times, it's just like A, it's just a central simple algebra A with different K structure given by the Frobenius. So these two motives are isomorphic. So when you take M equals 1, you get twisted Grassmannians. So this is the twisted Grassmannian for A, and this is the twisted Grassmannian for B. These motives are isomorphic. And when you take D equals 1, you get the motive of Severi-Brouwer for A as isomorphic to the motive of Severi-Brouwer for B. Okay, so this is the interesting example, basically because Karpenko in his paper showed that this cannot happen until B is either A or A opposite, when you take lambda to be a Z coefficient. Okay, so whenever the coefficient ring is Z, this cannot happen unless B is A or A op. But then you can always find a central simple algebra of order not dividing p square minus 1 in the Brouwer class, and you get examples of varieties whose motives are isomorphic for any finite field coefficients, but not for Z coefficients. Okay, so this is interesting example. And some open questions here. Again, all of these results hold only when G is inner. I haven't analyzed the case for G outer. So are the motives isomorphic even when G is outer? And also in the generic criterion, I said like X was projective homogeneous, Z was arbitrary. What if I make both X and Z arbitrary varieties? Does the generic criterion still hold? We don't have any counterexamples, and I don't know if it is true. So I'm just thinking about this problem. Okay, that's it.